Good evening, ladies and gentlemen. My name is Howard Nye. I'm the chairman of the Space Group of the Royal Aeronautical Society. I was the former president, and I'm a former ESA department head as well. Welcome to this Space Group lecture, the ESA JUICE mission to Jupiter and its icy moons, presented by Giuseppe Gisari and Olivia Latas. Thank you very much, gentlemen, for coming, being here with us today. And our thanks go to Airbus for sponsoring this event, without which we would not be able to have such a good event. I have to first make some housekeeping announcements. There will not be a fire alarm test in the building today, so if the alarm goes off, we all have to leave the building. And the assembly point is outside the building towards the Intercontinental Hotel. And RAeS staff, the staff from the Society, will be there to guide you. If you have mobility or access problems, please make sure yourself known to a member of the staff so that they can make necessary arrangements for your safe exit. Hopefully we're not going to have an alarm, so we move on. Please don't leave any unmarked bags or other items unattended. Please switch off your mobile phones, which is what I'm going to do myself, so we don't annoy the speakers. The event is being recorded and will be available on the Royal Aeronautical Society YouTube channel, which is very, very good. After the presentation, there will be an opportunity for questions with a microphone, so if you raise your hand, and we will have a microphone brought to you to raise your questions. First, then, I would like to introduce Mr. Patrick Wood, the Senior Vice President of the Space Systems UK at Airbus. Airbus was the prime contractor of this mission to Jupiter. Prime contractor means responsible for coordinating all of the other industries and delivering the spacecraft and its payload. So if you'd like to make a quick brief, thank you very much.
Thank you very much. Well, thank you. I promise I'll be very brief. I'm here just as much as you are to hear the lecture, so it's such a fantastic mission. But I just wanted to give you a little bit of a UK context on some of the work that we did to support the program. So JUICE mission. My role in Airbus, I have two roles. I'm head of space systems in the UK, but I'm also head of all the assembly, integration, and test across Europe. So the teams in Friedrichshafen, Toulouse, Baracus, and Stevenage. Stevenage was mostly on the AOCS from a system study point of view, but the actual manufacturing was done in many of the sites that come under my responsibility. So, and I got the real opportunity of seeing JUICE just at the end when it was just getting ready to be shipped to the launch site. And I can tell you, it was an amazing spacecraft, and I'm really looking forward to hearing more of the detail of that. So, we did quite a lot of missions. So this is a very UK-centric slide. So. We do a lot of missions across Europe, but I think in the UK we're really proud to support some of the work that goes on. So JUICE is currently one of the topics that the UK team and Justin Burns' team up in Stevenage did a lot of the AOCS work on. But we also work on quite a lot of others, as you see. The consortium that we led within Airbus, so Airbus prime contractor, 80 companies across Europe, and I think this is what, for me, European Space Agency projects are all about. It's about working collaboratively across Europe, lots of suppliers, lots of people coming together to make a mission so that the European Space Agency can deliver these fantastic missions. Just a tiny little bit on the plugging our factories across Europe. So, you know, we're across Europe. In the UK, the team was based in Stevenage. But as I say, I know for the last 6 months before we shipped it to the launch site, we had a day-by-day plan for getting the JUICE mission to the launch site. So the team were really under a lot of scrutiny and pressure to get there. But actually, the team performed extremely well. Not just Airbus, but all of the consortium coming together. A few interesting bits of stats for those that love statistics. The spacecraft's about a 6-ton spacecraft, so for space exploration, that's a very large spacecraft. I've certainly not seen something quite as large as that. And 60% of that is fuel. So that's, again, really, really different different model, and the 10 instruments only weighed 220 kilos, although when you saw the actual spacecraft, it did look like they were heavier than that. So I think without further ado, I'm just here to do the warm-up act, really, just to hand over. So without further ado, I will hand over to yourself. I was going to hand over to Giuseppe.
Well, thank you very much. Thank you for your support in this project and this discussion. So I would like to introduce our two speakers today, Mr. Giuseppe Sari, who is the project manager of the JUICE project. He is responsible for implementation of the project, dealing with industry, making sure that all of the industrial partners are working together and providing definition of the requirements and reviewing and making sure that the spacecraft is built correctly and launched correctly. Big responsibility. Our second speaker is Mr. Olivier Vitas. He's the project scientist for this mission. The project scientist has to deal with all of the scientific objectives, talk with all the principal investigators, make sure that everyone is working together, coordinate the delivery of the instruments on board. So it's a really big responsibility as well. And after the launch, of course, the project manager has to make sure the spacecraft is working properly and then goes into the operational phase, and at which point the project scientist is leading the results of the scientific instruments. So the time is yours, gentlemen.
Thank you, Mr. Chairman, and thanks everybody for coming here for this talk about JUICE. So we will talk, I will do an introduction, a little bit of an introduction, then Olivier will talk about science, then I will come back to talk about engineering of the spacecraft, and the conclusion will be on Olivier. First, for those maybe less familiar with ESA, ESA is the European organization which is the gateway to space. We have something like 5,000 among staff, a contractor, 22 member states, and the purpose is to do exploration, to develop the space and the space industry for only peaceful purpose. So we do not do military or any other kind of spacecraft. We have an headquarters in Paris. We have 7 sites all around in Europe. We have our spaceport, French Guyana, from where we launch our spacecraft. And myself and Olivier, we come from ESTEC in Norway, in Holland, where is the technology center, so where the program are managed. And how much do we spend of taxpayer money is typically 5.7 billion per year. Out of those, around 500 million per year, so 8% is for scientific program. This is the ESA fleet in the solar system. The science mission has 2 big elements. One is the exploration of our solar system, and the other are the astronomy mission. And those are the mission which we do, the spacecraft that we did to explore our solar system. As you can see there, we move from the Sun up to now Jupiter was the last one, and Cassini, with the mission Cassini-Huygens, we went to Saturn some time ago. And today we talk about JUICE. JUICE is stand for Jupiter Icy Moon Explorer, and this is a mission to Jupiter and to 3 of the Galilean moon, Europa, Ganymede, and Callisto, and is the first large mission of the science program's Cosmic Vision. Now, what does it mean, large mission? Large mission means not only a big satellite, as was said by Patrick, but is also an expensive spacecraft. And large mission is, we have 3 kinds of mission in the science. The large mission with a budget of around 1 billion euro. The medium mission with a budget around, let's say, 600 million euro, and then maybe sometimes higher. And the small or flexi mission with a budget of around 100 million euro or less. And in particular, the JUICE mission, when I talk about 1 billion euro, is to make the spacecraft, to procure the launcher, to procure the ground segment, but not the instrument. The instruments are funded by the National Space Agency. And if we put together the cost of the mission on ESA side plus the nationally funded cost of the mission, we arrive at 1.6 billion, more or less. Overall timeline, the first idea of the mission, they started in 2007. From 2007 to 2014 was the so-called study phase. In 2012, the mission was selected, means it was decided to study it. In 2014, the mission was adopted, so it was decided to build it. Then from 2015 to 2023 was the industrial phase where I was involved. And our industry, Airbus Defence and Space, they built for us the mission, the instrument team, they built the spacecraft, sorry, the instrument, and we put them together, and eventually we launched in 2023, was April this year, with an Ariane 5 launcher. A launcher is the one before the last Ariane 5. We are now completing the commissioning, which is we switch off the spacecraft, we check that everything go well, we update the software where necessary, and that will be finished in July. And after that, the cruise, which is the traveling to Jupiter, which will take 8 years, is starting. Arriving in Jupiter 2031, and then the nominal mission will be around between 2031 to 2035, plus possibly an extension. And now just the end for the project, at the beginning for the science, is the launch with Ariane, the décollage. So that took place the 14th of April. The first attempt didn't work because the weather was bad on the 13th. And then on the 14th, we managed to launch. And now, Olivier, we talk a little bit why we do this kind of mission.
Okay, so Giuseppe mentioned the name JUICE, Jupiter Icy Moon Explorer. So we want to explore the moons of Jupiter. So why Jupiter? So this chart shows a comparison between the different moon systems in the solar system. So if we start on the left, we have our moon. Then on Mars, we have two little moons, Phobos and Deimos. Then if I jump to Saturn, many moons, of course, with Titan, very interesting moon. And then Enceladus, another one. Uranus, you see how it looks like, the distribution, 5 medium-sized moons, which are also quite interesting. Around Neptune, there is a moon which is called Triton, which is also a very interesting object, maybe a Kuiper belt capture object around Neptune. And Pluto, also a small moon system. But when you look at Jupiter with these 4 Galilean moons, so Io, Europa, Ganymede, and Callisto, you see that the Jupiter system in terms of moon, it's very special, very interesting. So if we are interested in the moons in the solar system, Jupiter is a very interesting target. So that's why we go there. From the distance to Jupiter, we have Io, Europa, Ganymede, and Callisto. Io very close to Jupiter, so embedded in the strong radiation environment, so very difficult to explore. We are not going to observe too much this moon, so it's quite interesting, and we are mainly interested in the 3 next moons, so Europa, Ganymede, and Callisto, which are the icy moons in the Jupiter system, and our prime target will be the Ganymede moon. So why Ganymede will be our prime target? So if you have one thing to remember about JUICE, we'll explore Ganymede in details. It's a very unique object in the solar system. The biggest moon of Jupiter, the biggest moon in the solar system. When you look at the surface, many craters, many different features, black terrain, light terrain. So looking at the surface, and you see how complicated is the surface, you can really derive the history of this moon. and to understand the evolution. And to understand the evolution of moons and planets in the solar system, it's very important to understand it. So this surface already shows that a lot of interesting features have been happening on Ganymede. In the interior structure, so this is what we think Ganymede is made of, but of course JUICE will revisit this picture. So in fact, after the JUICE mission, there will be a new chart giving more details on this interior structure. And one of the most interesting aspects, if not the most interesting, is this light blue layer here, sandwiched between an ice layer here, this is the icy shell, and an ice metal here, and this is a layer of liquid water. And we have good evidence that there is liquid water from previous missions and from ground-based observations, so it's quite fascinating to think that there is a liquid layer underneath the surface of an icy moon like Ganymede. And there is probably more liquid water here than on Earth. So that makes this object very interesting. And of course, one of the big questions is whether life could have started somewhere else in the solar system. And to look for habitability and possible search for life, you need to look for, the first ingredient is to look for liquid water. That does not mean that there is life here. JUICE is not equipped to detect life, but at least we will understand better the properties of this liquid water. At which distance on the surface do we have this liquid water? What is the depth of this ocean and what is the composition? So that's very interesting aspect of this moon. In the middle, we have an iron core, which again does something very special. It generates its own magnetic field. So that's the only moon in the solar system for doing that. And in terms of solid bodies, we have three bodies. We have the Earth, and we are happy to have our own magnetic field. We have Mercury, and we have Ganymede. So what is the role of this magnetic field for Ganymede? How does it interact with the huge magnetic field of Jupiter? A lot of questions that we would like to understand with JUICE. So that Ganymede, it's a very interesting object and our prime target for the JUICE mission. But of course, we don't only focus on Ganymede. We looked at the other moons as well. And to understand the similarities and differences between the moons, it's also very, very interesting because they are very diverse. So we have Io here, Europa, Ganymede, and Callisto. If you are interested in rocky moons, you have to focus on Io and Europa. Ocean moons, it's Europa, Ganymede, and Callisto. So those moons harbor an internal subsurface oceans. For Europa, we are sure. Ganymede also. Callisto, there is a question mark. So when there is a question mark, it's always interesting to send the mission because we will try to answer this question mark. If you are interested in origin and formation, Callisto is a prime target because given the so many craters on the surface, we know that this surface has not evolved over the last 4 billion years. So this image is the one which was at the beginning of the formation of the Jupiter system. If you look at this image, it's 1 day old because of the so many volcanic eruptions. This image is only 50 million years old, and this one is 4 billion years, and Ganymede is in the middle. Resonance of Laplace, this means that the orbit of the moon, they are locked between each other. So when Io is doing 1 rotation, Europa is doing 2, and Ganymede 4. But also Ganymede and Callisto, they are kind of locked between each other. So that makes it's very interesting in terms of dynamics. Orbit is also a very interesting topic in science. In terms of active surface, it's Io with the volcanic eruption every day, and Europa with the recent resurfacing of the ice. In terms of habitability, it's Europa and Ganymede because of their subsurface ocean. And in terms of search for life, Europa is currently the best target in the solar system. So you see they are all different, very diverse system, and with JUICE we are going to know more about that. But we are going not only to look at the moons, because if you want to understand whether a moon is habitable, you need to understand the full system. Why around a planet like Jupiter we could have find an habitable place, and that means we are going to study the Jupiter system in detail. So the giant planet. So here the colors indicate different boundaries conditions in the plasma environment of Jupiter. So we are going to study the system in detail, and in particular how we have some couplings or links between the different bodies. There are some couplings from the gravitational point of view between the moons and Jupiter due to the gravity. And one outcome of that are the tides on the moon. So the shape of the moon change and heat inside. So it's one possible mechanism for the generation of liquid water. So the link between Jupiter and the moon, it's very interesting to study in terms of gravity, but also because you have the huge magnetospheric system in Jupiter, there is also a link, invisible link between the moons and Jupiter via the magnetic field line. And that we would like also to explore to understand what is the role of those links. So it's, in terms of physics, it's extremely interesting. And this is one of the illustration of this invisible link between the moons and Jupiter. And these are the aurorae. So you may have seen these images from the Hubble Space Telescope, where you see the aurorae on the north pole of Jupiter. But part of these aurorae are due to the moon. Here, this is the footprint of one of the moon, for example, Io. So we have particles which travel from the moon to the Jupiter via the magnetic field lines. And this creates aurorae. So we have aurorae for Io, for Europa, Ganymede, and possibly Callisto. There is another question mark for Callisto. So Callisto also quite an interesting object. So we are going to study that also in detail with JUICE. And just to give you the things, the perspective of how big is the Jupiter magnetosphere. So if we'll be able to look with our eyes to the magnetosphere of Jupiter in the night sky, so you see how big it is compared to the full moon, for example. So it's probably the biggest object in the solar system, which goes beyond the orbit of Saturn. So a huge object. And we are not going to do only planetary science with JUICE, which is great. In terms of planetary science, it's already, I think, a fantastic mission. We study the interior of the moon, the surface, the subsurface, the atmosphere, the magnetosphere, magnetic field, Jupiter, the evolution of the solar system. But because we do also a link with the extrasolar system. We up to now we have discovered more than 5,000 extrasolar planets, and a significant part of them looks like Jupiter. So studying Jupiter is also make us understanding much better the other solar system. And later, when we will discover moons around the exosolar planet, we will pretty sure we'll be using the knowledge of JUICE about the icy moons to understand better the moons in the extrasolar system. So there is an interesting link also with the exoplanet community. Here, this is shortly after launch, we have released the first images. So we didn't have to wait 8 years, also a few tens of minutes after the launch, we got the first images on JUICE. They are based on the monitoring camera, so it's an engineering camera that we have put on board to monitor some critical deployment. And I think a lessons learned, maybe Giuseppe will comment about that, it's good to have those cameras on board. First, because it's fun, we can have some selfies. So this is the selfies of JUICE. So shortly after launch, so you see the Earth. This is part of JUICE. So here it's a radiator of the imaging spectrometer. Here with the other camera, we could see shortly after launch the radar antenna which were stored. Another image here, we see a Langmuir probe here, another moon. Here we could see partly the deployment of the solar panel. So that was useful to see that the solar panel were properly deployed. We had the right telemetry, but it's always good to check what happened with images. Here we saw the upper stage of the Ariane 5 in the background, and here that was a few days later when we wanted to deploy the radar antenna, and we saw that it was stuck. It was good to have the engineering camera to check what's going on, but Giuseppe will mention more about it. And I will leave the floor to Giuseppe.
So now we know why we go to Jupiter and what we want to do from a scientific point of view. Now a few considerations. Number one, to get there is not straightforward, because if we launch something, the gravitational pull of the sun will bring it back. And we don't have a launcher which is powerful enough to shoot the JUICE directly to Jupiter, because it will take a couple of years to get there. So we need to do what? We need to do gravity assist maneuver, which means the spacecraft will fly by the inner solar system planet. How many, it depends on the mission. And by doing that, the spacecraft will increase its energy, so it will increase its speed until it has enough speed to escape the gravitational pull of the sun and get to Jupiter. So we launch April this year. 23. Next year, in August 24, we will have the first gravity assist maneuver, would be a Moon-Earth gravity assist. It will be the first time that we do a Moon-Earth gravity assist. In September, in August 25, the spacecraft will come back and do a Venus gravity assist. September 26, back to Earth for a Earth gravity assist, and January 29, the last Earth gravity assist. So 4 flyby, which means that we launch in this year, and in 29 we are still here around, but we will be here with enough speed to get to Jupiter. And getting to Jupiter will take 2.5 years with arrival in July 2031. And there is the Jupiter orbit insertion. Now, when we arrive in Jupiter, we will be so fast that we will miss the moon, the planet. That's why we have a main engine, which is mainly there to brake. So we will turn the spacecraft, point the main engine in the direction of the speed, and burn the main engine for 1 hour, burning something like 1 ton of propellant in order to brake and to be able to enter the orbit of Jupiter. And then from there on, there will be the scientific mission. Scientific mission means 35 flyby of the moon, each one with measurement. So I think we will have 15 of Ganymede and something like that of Callisto, and only 2 of Europa, because the radiation environment is too extreme. And the end of the mission would be to enter in orbit around Ganymede, would be a polar orbit, 500 kilometer altitude, maybe less, which will allow, therefore, while the spacecraft is doing the polar orbit, the moon will turn, and we will be able to have a complete mapping and tomography of the moon. End of the mission, 2035, and I'm sure that if we will have enough fuel, we will continue the mission. Now we know how to get there. There is, however, this chart, I'm not going to go all the details, but it's only there to let you understand which were the driving force to do the spacecraft. The first element is that being in Jupiter, there is very little power, because the solar flux is only 50 watts per square meter, and therefore you need to design a system which is using not very much power and is able to collect power. And since our technology is mainly solar array, we need to have an extremely large solar array. If you consider 50 watts per square meter, consider the efficiency of the cell, what the power which is lost during the transformation. At the end, we generate 8 to 9 watts per square meter. That's why we have 85 meter solar array. Second element, high and low temperature. Jupiter is very cold. We are going to be at minus 220 degrees. But since, unfortunately, to get there, we need to do a Venus flyby. At Venus, the spacecraft will be very hot. And therefore, the thermal design has to be done in order to cope with extremely hot temperature, like more than 150 degrees, and extremely low temperature, minus 220. There is an harsh radiation environment in Jupiter, because there is harsh radiation environment in space in general, coming from the space, coming from the sun. In Jupiter, we have the radiation coming from Jupiter, from Io, which is an active moon, and all is collected by this huge magnetic field of Jupiter and stay there. Therefore, the spacecraft has to be designed, components selected in such a way it can survive with this harsh radiation environment. And this is one of the biggest difficulties that we have. Then the spacecraft has to be very sensitive. The instruments that we have are very sensitive to, they are very sensitive instruments, and therefore the spacecraft has to be very clean for the electromagnetic point of view. And that is introducing also a difficulty, because we have elements which are generating magnetic field or electric field. We have the solar array, we have the power system, we have the reaction wheel, we have many other subsystems which by definition generate magnetic field. So the effort to screen and to reduce by design this generation of field was also very important. Then the navigation and the autonomy of the spacecraft is also a big driver. First of all, doing all this flyby require a very accurate navigation system. But very important, when we are in Jupiter, the turnaround time of the signal is 1.5 hours, more or less, in average, which means if we send a telecommand to do something, and then we wait the response of the spacecraft saying, yes, I did it, it takes 1.5 hours. This is killing any kind of real-time operation. We cannot do a real-time operation of JUICE in Jupiter, which means that the spacecraft need to be very autonomous in terms of things which has to do, which of course will be pre-programmed, and also in terms of reacting in case of problem. And last but not least, we need a large amount of propellant. It was said by Patrick is 3.6 tons of propellant, which means it's very special design, 2 big tanks, a big structure, which however need also to be very light. So all that together certainly generate a lot of headache to the engineer, but I think it did, so far it did work. And then we have this spacecraft. As you can see, big solar array, big high-gain antenna, again, because we are very far, so we need a big dish. And by the way, this high-gain antenna is also a thermal shield when we are to Venus. All the instruments are on those sides, which is the native size of the spacecraft. And this is the way it will look more or less in orbit. We have 10 instruments, as I said, procured by the national agency. We have the instruments are built by the instrument consortium led by a principal investigator. We have here one of the instrument PI for JMAG. And these 10 instruments are divided in 3 groups. The first group is a remote sensing. I would say the instrument to look in some band of the electromagnetic spectrum. Oops. Yeah. So we have an optical camera, we have an infrared spectrometer, there is ultraviolet spectrometer, and there is a sub-millimeter wave instrument. The sub-millimeter is looking to atmosphere, is able to pick up the, for example, the line of the water. This instrument was recently pointed to Earth and confirmed that there is water on Earth. Then we have a geophysics instrument. We have a laser altimeter. With the laser, we will be able to measure the profile of the moon. We have a radar, the infamous RAeS that was blocked for 2 weeks. We could not deploy. And this is used to measure the depth of the ocean, the thickness of the ice. And we have also an instrument which will be able to measure the gravitational field. Basically, it will measure the variation of position and speed of the spacecraft induced by a varying gravitational field. And then we have 3 in situ and particle instruments that will measure electrical field, magnetic field, plasma environment, electron, proton, heavy ion, all the stuff that you find in space. Few pictures. Now, sorry, we have to test the spacecraft before launching. And this is called qualification and acceptance test program. One important test is to put the spacecraft in a thermal chamber, make the vacuum, switch on the sun, and that test will confirm that the spacecraft can survive in vacuum, can survive when there is the sun. Then we also switch off the sun and we let some liquid nitrogen flow into some panel, which will simulate a very low temperature. So we did that test, and of course the spacecraft is switched on and will work. With this test, we confirm when the spacecraft is in flight, will work. Of course, we also need to confirm that when we switch on the spacecraft, it will work and will not subject to plenty of an interference, that one instrument will not work because we have a direction wheel ongoing and so forth. I like this picture because you see all the antenna which we have in the spacecraft. This is the high-gain antenna. Basically is used for, mainly when we are in Jupiter, to transmit a high data amount of data. So it's very big because we are very far and we need to transmit a lot of data. We have a medium-gain antenna, this black one, because when we are in Jupiter and we do the measurement, the high-gain antenna will not look to Earth, and we need always to be in contact with Earth. So this medium-gain antenna can be steered in 2 degrees of freedom and is always pointed to Earth. Then for the phase in which we are close to our planet, we have 2 low-gain antenna, one on this side and the other one on the other side, which essentially they were used to the initial acquisition of the signal from the spacecraft when we are close to Earth. Then we have this big RAeS antenna. We'll come back to this is to measure the depth of the ocean. This is very long, and I will come back to this. Then we want to test the spacecraft to make sure that when we launch with the rocket, the vibration induced by the rocket is not breaking the structure. And we do 2 kinds of tests. One test is a shock test. The shock wave is generated when there is a separation of the spacecraft from the rocket. And the spacecraft is connected to the rocket via a clamp band, which is open with explosive actuator and generate a shock. So this test is called clamp band release, and we just do that on ground. Then, of course, we need to put the spacecraft on a shaker, which is generating a sinusoidal vibration on the axial direction and on the in-plane direction, so three directions. And with this set of tests, we are sure that when we launch, the load coming from the launcher, the direct mechanical load, are safe for the spacecraft. But it's not all, because the rocket makes a lot of noise. And this noise is generating, of course, waves. And these waves generate vibration, which are called random vibration. So it's not a sinusoidal, but it's a random. So we put the spacecraft inside this chamber, and we just generate a huge amount of noise. We are talking about 140 decibel. And that will demonstrate that the spacecraft will also survive the vibration induced by the noise of the engine of the rocket. And then, of course, before doing all this, we need to operate the spacecraft before, we do the test, and we operate the spacecraft after to check that everything is still like before. And one of the critical things is a deployment test of the solar array. And you see here the inline deployment of the solar array, and you have here a picture of how big the solar array is with respect to the people in the foreground. We delivered the spacecraft to the Cayenne airport in French Guyana on 9 of February. Delivery is with the Antonov 224, is the big transporter that we have. As you can see, this is an Ukrainian spacecraft. In the past, we had availability of Ukrainian and Russian spacecraft, aircraft for the transport. The war induced also a problem on our transport, because we did not have any more the Russian aircraft, and the Ukrainian ones, they were all taken by NATO to do military operations. So there was the risk that we did not have a transport. But eventually we managed to have it with a little bit of delay. This is the spacecraft in the payload preparation facility in French Guyana, the last touch before being integrated on the spacecraft, on the launch. Now, a dream of a project manager is to have a spacecraft without any mechanism, because mechanism is a risk. Software you can change, mechanism, if you're stuck, you're stuck. And you see here all the mechanisms. Those are the solar array deployment. Each panel has its own mechanism at the beginning. Then you will see here now, this, of course, the mechanism is to rotate. This is the deployment of the medium gain antenna, mechanism which have to work in 2 degrees of freedom. The RAeS antenna, 16 meter, two antenna, each one with 4 elements which you need to deploy. You see how complex was the deployment there, and this is what we went stack. So it's a very complex sequence of deployment. And then, as we were not happy, there is also a 10-meter long boom. And on the 10-meter long boom, there is an antenna made by 3 small boom. And then we have 4 language probes, which are 4 other antenna there. So it's really quite an impressive amount of antenna that, of course, we have to have in order to have the mission. And that is the flight configuration, and this is the configuration where now the spacecraft is. Now, the unfamous RAeS antenna, so the boom which was blocked, generate, I don't know whether maybe one of you has followed that, but for everything went well with the exception of this final antenna, and the first boom that we try to deploy basically were blocked. But eventually, with some additional work, some trick, with the help of the camera which were on board, we managed to deploy. And in this GIF, you can see really the deployment of the antenna. And let's see whether it's coming back. So so here you see the boom is moving. It's doing something very strange, because the initial idea is to deploy one segment after the other, but now we have to deploy all together. But eventually, it was deployed, and it's nice. When we saw that, was nice. And then this is a camera, so it's not a camera taking a movie, but a set of picture. But you see, this is the deployment of the language probe, so one of the last antenna which we deployed. And this, we managed to monitor and to understand what's going on thanks to these 2, I would say, public relation camera that we had on board. And you see here, we also had one instrument which was an accelerometer. And this instrument was able to measure the various phase, the various shock induced by the deployment of this antenna here. So this is the antenna, and this is the radiator of one instrument, and this is the edge. This is the edge of the solar array. And I think the next one is a nice animation of the future, and I will let Olivier to discuss about it.
Yes, so you have seen with Giuseppe, we are a very great spacecraft. Everything is deployed, the instruments work well, we are checking at the moment all of them. We will finish this check in 2 weeks, and then we'll be ready for the cruise phase. So Giuseppe also mentioned the long cruise phase, 8 years to go to Jupiter, so we have to be very patient. That's one of the problems when we work in planetary missions. You have seen the timeline, 30 years, so we see a carrier activity. So what will happen in 8 years from now, so 2031, we will enter into the Jupiter system. And every month, there will be an orbit around Jupiter where we get close view from the giant planet. And every 2 orbits, there will be a flyby of one of the moons, either Europa, Ganymede, and Callisto, a few hours before going close to Jupiter, or a few hours later. So during the 4 years of mission, there will be always something happening. I think we will keep the scientific community happy and entertained, that's for sure. And one thing which is also quite interesting in terms of navigation, and I will replay this animation, is that Giuseppe mentioned that we'll switch on the main engine to brake the spacecraft to make sure it's captured by the gravity field of Jupiter. But before, a few hours before, we'll make a Ganymede flyby. This time not to accelerate the spacecraft, but to decelerate the spacecraft. So in terms of navigation, also I think it's the first time we are going to do that. We do a very close Ganymede flyby, a few hours the capture into orbit around Jupiter. So in terms of challenges and navigation, there is really also a lot with JUICE. So I will, very exciting mission. I will finish with that, showing that, of course, you can always follow the news on Twitter, the webpage. We are also going to release a 2-hour movie in September, October called The Making of JUICE. It will be on YouTube, and you will know more or less everything which is behind the scene. So you will learn more also about the human aspect of this project, which I think is so quite interesting. And I take the opportunity to thank Giuseppe and his team to have made a great spacecraft, and we are very happy to start the cruise and in 8 years the nominal mission. Thank you very much.
Well, thank you very much. It's a fascinating mission, and lots of challenges in getting it up in orbit and operational, and now a huge extent of science to come. Now, if we have questions from the floor, please use the microphone over there. If anyone would like to ask any questions?
I have 2 questions, if I may. The first one is the spectrometer that's being carried on board for the determination of the atmospheres. What form of spectroscopy is that? Or is it a hybrid of a number of...
We have different instruments for spectroscopy. First, we have visible and infrared imaging spectrometer. So at the same time, we take images in different wavelengths, in the visible and in the near infrared. So that's to get the information on the composition of the surfaces of the icy moons, but also on the atmosphere of Jupiter. So that's one thing. So imaging spectrometer, so image and spectroscopy at the same time. Then we have a UV spectrometer to do spectroscopy in the ultraviolet. So it's also quite interesting for the exosphere, so the tenuous atmosphere of the moon, the aurorae on Ganymede, the aurorae on Jupiter, and also we can get information on the surface of the moon, so UV. And we have also a very specific instrument, which is the submillimeter wave instrument. So here we look at different wavelengths, so gigahertz, so 600 and 1200 gigahertz. And we do also spectroscopy in this regime to get information on the atmosphere, so temperature, composition, and velocity. So it's in terms of spectroscopy, it's quite a rich range, I have to say.
Second one. In terms of the mass of the craft and of the propellant that's being carried, so if I was following correctly, more than half of the mass is propellant. What are the consequences of that in terms of having to provide additional energy to carry so much propellant? So.
Yeah. So. In fact, the is something that you have to pay, in the sense that the propellant is necessary for doing deep space maneuver, for Jupiter orbiting station, Ganymede orbiting station. This is the amount that you need, and you have to find a reasonable balance, trying to minimize then the mass of the spacecraft. and in particular of the structure. In fact, one of our biggest headache was really to design a structure which was light enough, but strong enough to bring 3.6 tons of propellant. But this is the propellant that you need, in fact.
Another question over there.
I'm just thinking in terms of the actual moons itself, in terms of how complicated they are. So do you think the additional science or the new science will lead to any reclassification?
Well, in terms of classification, I don't think there will be a change. What is very important is to really characterize in details those moons, in particular Ganymede. We don't know much about it. We would like to know the interior structure, in particular where is this liquid wire, what is the composition, the core, the magnetic field, the surface, the atmosphere. We do a little bit the same at Europa. Also, we have only 2 flybys, and also we do that at Callisto with the 21 flybys. So the main goal is to know more about those moons, in particular to have a complete tomography of Ganymede. In terms of classification, I don't know what will change. In terms of classification, there is the classification of the planetary protection, whether our moon is better protected in terms of the search for life. That's the main classification I can think of that could change depending on what we find. But with the information that we have available, I don't think that the classification will change. And in fact, for us, it's better if it will not change, because depending on the classification, you're allowed to crash on the moon or not. So we are allowed to crash on Ganymede. We are not allowed to crash on Europa. So if the classification changes for Ganymede, we are a bit stuck with the mission.
Probably when we will know that on Ganymede there is life, we already crashed.
Yeah.
Any other questions? Question over there. Thank you.
Hiya. Just thinking about when the beam got stuck, what was the situation on the ground? I mean, was it extreme worry, or was it business as usual? You know, we've got systems in place to deal with this.
When the Ariane was stuck, the situation on ground was reflecting people's spirit. Someone was extremely worried. Someone was more optimistic. Let's say that the good things is that, as Olivier said before, we had this monitoring camera which allow us to understand after, let's say, 1 week, where was the problem and what could be the cure of this problem, and also this accelerometer that allowed to measure the various shock. Then we had several ways to take the problem, because the reason why it was probably a pin which was not retracting properly, therefore not releasing a spring. And the reason could have been thermal reason, because this part of the antenna was a minus 80 degree. So probably a combination of thermal reason together with tight tolerance and a little bit of unluck. So in fact, eventually what we did was to not only to operate a non-explosive actuator which was still there to be operated, which generated the shock, but we did that after exposing the spacecraft to the sun, such that we could increase the temperature to basically 20 degrees. So it was a combination of things. Of course, the first things you are a little bit shocked and scared, but there are always means to solve the problem.
Question at the back?
Yes. Hi. I was curious, given the extreme power requirement, were RTGs ever considered? And if so, I don't know if you could comment a bit on the trade-off there and what decided you to go that way.
First, we do not have this technology in Europe, not in ESA. This is the first things, and in fact, the not having this technology limits us to exploring up to Jupiter, I think. Otherwise, we need to go with someone like NASA which has this technology. This is the first element, and today there are, we start moving in that direction to develop this technology, but today we don't have it, so there is no trade-off. And number two, as per our, I don't know whether to call it mandate of convention, we cannot launch radioactive element in space. We cannot launch a block of plutonium, of uranium from CSG, from French Guyana. So also that has to change. So we really could not do anything with the RTG.
Any other questions? Right at the back, and there's one on the table first. Yes.
How do you use JUICE to work out the composite, what the planet's made of? You said it was water and ice. How do you use JUICE to work out what is in it?
Yes, so it's a very good question. So there are different possible measurement to get the interior structure of a moon. First, the gravity experiment. We have an experiment called radio science. So we measure precisely the position of the JUICE spacecraft doing a flyby or around the moon. And this position will tell us something about the gravity field of the moon. And if you get the measurement of the gravity field of the moon, you can get an information on the interior structure, because the interior structure will drive the gravity field of a moon or a planet. So that's one thing. For this liquid layer ocean, we have different measurement technique. One is will be done by our PI in here, the magnetometer. Because the liquid water is salty, plus the moon is embedded into the large magnetic field of Jupiter, so those two ingredients makes that you can measure some disturbances in the gravity field around the moon. And from that, you can get information on the liquid layer. It's quite a complex technique, but it works, and Michel will use it to get even more information on this liquid layer. So for magnetometer, you can get information. Then we have also another very special experiment, which will use a laser altimeter. So we will shot lasers on the surface of the moon, and we'll measure the topography of the moon. So if you have little hills, craters, but we will repeat those measurements, and then we will see how the shape of the moon change with time due to the tides. And those measurements also indicate what is in the interior of the moon. So the thickness of the icy crust, whether there is liquid layer. So we have many different techniques to understand the interior structure, which is quite interesting when you think that you get the information on the interior while you are at a few hundred of kilometers above the moon. But it's possible, and we are going to make use of it.
The timescales of the mission are extremely long, a little like Rosetta before it. So, from the initial inception through to conducting science is a substantial part of people's careers. You might, many of those involved will have retired by the time this gets there, or will have moved on to other things. And some of the engineers who will come in and do that operation when it's in orbit will be in school right now. Have you had to take any particular measures to accommodate that lifespan?
Yeah, no, it's part of the, I don't want to say part of the game, but part of those projects. You have seen this timeline. I mean, the Rosetta mission was long, as you said. The Cassini-Huygens mission was long. The JUICE mission will be very long. So the human management is very important. You have to make sure that when you arrive, you have the right people which are trained. So indeed, some of the people who will analyze the data in 10 years from now, they are still at school. They still don't know that they will analyze the data, but hopefully they will join the teams. What is important is that also we select the people such that they can also follow the project for a major part of it. For example, Giuseppe could follow the full project as project manager. He will retire in a few months from now, so that's perfect timing, perfect human management. In my case, I started the project in 2015, at the beginning of the development phase, because the previous study scientist
could not follow the rest of the project. He was going to retire a few years after, at that time. So they were looking for someone who could follow the project from this stage to the end of the mission. So they were looking for someone born in around 72, and I'm born in 72. So you have to select the people at the right stage, but also you need to make sure that you will train the people at the right time. And that's also the task of the project, but also all the PI teams. So I count on Michelle to make sure that she will have the right people at the right time, but that's part of the project.
And anyway, we know that this kind of project, 20 years, there will be not a single person from the beginning to the end, so is a fact for this kind of mission. And in particular, what is critical, I think is a very good question, is the operation of this mission, that the people operating today, they will not be there to probably to operate the mission when it is in Jupiter. That's why a very important document that we have is the user manual. We have user manual of the spacecraft. You can think that if you have a washing machine user manual, it's already difficult to understand, and it's 20 pages. But the user manual of the spacecraft is few thousand pages. And one of the tasks that we have during this commissioning and during the first period is to make sure that this user manual is clear, that the new generation can understand the spacecraft by looking to the user manual and not rely on someone that maybe is gone.
One critical aspect is the trajectory. You have seen a little bit that it's quite complex, flybys, to orbit insertion and so on. And there is one person in the project who started in 2005 to already started to look at the Jupiter orbit around Jupiter. And he will be able to follow the full project until the end, because we need this kind of expertise until the end if we want to change the trajectory. And we may want to change the trajectory until the end. So there will be one person from ESA, he's called Arnaud Boutonnet. He was here from the beginning, and he will be until the end. So there are also some interesting case that someone could follow really from the beginning till the end.
Very good. Any other questions? On the left here. And then the last one will be over there.
Thank you. I just wanted to make a comment, and that was what a spectacular achievement the launch of JUICE, only a few months late, is. And it was testament to the team that Giuseppe led and to the Airbus team as well. This was built during COVID. You know, building instruments and spacecraft is difficult at the best of times, but in COVID times it was very difficult. So the instrument teams were really very lucky to have a team like we did. So thank you very much, Giuseppe.
Thank you.
And the last question over there.
Hi, did you do any specific developments for the ground segment? Is there anything special needed to receive the information back on Earth or control the mission from Earth, or do you just borrow time on an existing RF dish and that's all you need?
There is always a development, some level of development that need to be done, but in the specific case of JUICE, we could rely a lot on the development which was done for previous mission, in particular Rosetta and Bepi Colombo. Therefore, we will reuse a lot of software, but there are a lot of specificity that needed to be considered and require some adaptation, but we didn't start from scratch.
Very good. I think just to complete that, the European Space Agency has its own deep space network managed by the European Space Operations Centre in Germany, and that was built for the Rosetta mission, and presumably you're using the same infrastructure. Yes, yeah.
Well, in fact, we use three antenna of the deep space network. One is 30-meter dish antenna, one is in Sebreros, New Norcia in Australia, and the new one in Malarghe, which is in Argentina. So we can cover the complete visibility of the spacecraft.
Very good. Well, Thank you very much, gentlemen. It's a very, very interesting discussion. It's a wonderful project to be on, and we wish you continued success, certainly from the scientific point of view. And I thank you all for coming tonight. So now this is the close of the evening. We now are going upstairs for a small cocktail and a short interaction with the different people. It is kindly sponsored by Airbus, so thank you very much, Mr. Wood, for doing so. So if you'd like all to just go out of the door, we will show you how to get there. Thank you very much indeed.